We're doing grind 75 with C++. Let's jump into merge k sorted lists. So I don't know why this is marked as hard in the grind 75 or by LeetCode. It's really kind of a classic algorithm. It's a building block for a lot of things. It's used all the time in all the places. So for example, it's part of funnel sort. Pretty much anytime you've got multiple sorted arrays and you want to merge them, this is how you do it. So you are given an array of k linked lists. Each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. Now, it doesn't. The algorithm's the same whether it's a linked list or multiple arrays or some kind of ordered. Well, pretty much those are the main two. But in LeetCode here, it's a linked list. That doesn't change much other than the syntax. So whenever you're doing like a comparison-based sorting, you're looking at an upper bound of O of n log n. And the fact that each of the individual lists are sorted helps us get a little bit of a better runtime. It's going to end up being O of n log k. And that's because we're going to use, say, like a min heap, and the heap's going to have one item from each of the lists at a time, basically. Yeah, that's pretty much it. So let's jump into it. So a min heap in C++ is called a priority queue, and that's part of the queue header. So let's go ahead and add that. British spelling queue. So then now we need to declare it. Priority queue. The template arguments are kind of crazy, so let's step through it. The first template argument is going to be the base items. So we're going to want to put this list node type into it. So it's going to be, well, the inputs are pointers, so it's going to be pointer list node pointer. The next one is the container, particularly that's used for initialization. So it's going to be a vector of list node pointers. A little bit redundant, but that's how it goes. Vector list node pointer. And the third argument is the type of the comparison function. We have to use a custom comparison function because this list node structure is a little atypical. We want to compare this value field as opposed to, say, next. So we're going to do it by a custom function, and I'm going to use like a declare type keyword to just basically the type of whatever we pass into it. Now, what is this CMP? Well, we haven't defined it yet. It could be a function. In this case, I'm going to go for a lambda function. I think that's a good way to show off if you're like in an interview context. And it's not really harder than making a regular function once you get the hang of it. So the way that's declared is, I don't actually know what output type it is, so I'm going to use auto. And a little bit, it'd be better if you knew what the auto resolved to, but it's basically, it resolves to the type of the output, which in this case might be Boolean. So maybe it's actually Boolean. So compare, first thing, square brackets. What you put in the square brackets is variables from the enveloping function that you want to be available. So for example, if I put lists in here, then lists would be available inside the lambda function. I don't need that, so I'm going to leave it blank. Next thing, explicit arguments. So it's a comparison function, so by definition it has to take two things. And it's going to take two list nodes, pointers. List node pointer A, and another one B. And then now we define what actually it does. So there's a couple of things so looking ahead at what we're going to do, I see that these example inputs can be empty, or in this case, you can have a non-empty input, but the individual lists in the input are null. And that's kind of annoying, and I think more about edge cases than the actual algorithm. But for LeetCode, we have to deal with it. So how are we going to do that? Well, eventually, the idea is to put the head of each of the linked lists into the priority queue. And then we're going to continuously pop the top item off the queue, add it to our output, increment that linked list pointer, and then put it back in the queue. And now we see that some of them are going to be null. We know that the nulls are going to be either at the beginning, where if that's all it is, or maybe it could be at the end. By definition, this 6 always has a null next pointer. 4, 2, that's just, it's got to have something, and it's null by default. So we may have null pointers in the priority queue. So how do we want to do that? In order to not have to do a post check or a cleanup step, what I'm going to do is have the null values always float to the top of the queue immediately. So that way, when we're popping off, we can check then, and then just, skip a step if we get a null value. And that way, when we get a non-null value, it's always going to be totally non-null in the queue after that point. So what do we have to do? It's going to return a Boolean. And then, so first, I'm going to check if the inputs are null and handle those explicitly. So if A is null, what do we do? Well, the way the priority queue handles it is if it returns true, the left item comes first. And if it returns false, the right item comes first. So if we want a null A to come first, then we return true. And likewise, if B is null, we want the right item to come to the top, so we're going to return false. And then if neither of those is the case, we are going to do the actual comparison. And then that is our comparison. Now it's going to be a little hard in the example to follow if, say, which ones are the left and right arguments when it's actually doing a comparison. Is it always, say, the first input there? Or is it, say, whatever is already in the queue is maybe at the right argument and the new one's the left? Or is it vice versa? I actually don't know the answer to that. And it doesn't really matter for the purposes of stepping through. But if that's something, honestly, that's something I am probably going to look up later. But it's not strictly essential, I think, for getting the algorithm right. But it would be handy to know. Anyway, so end the declaration, priority queue. So we have to actually initialize our queue now. So it's going to take 2 arguments. This isn't calling the constructor. This is assigning it values. So since the braces instead of a parentheses. The first argument is the comparison function. So notice this is the type of the comparison function. This is a type. Oh, forgot the angle bracket there. This is a type. So it's all types in the template arguments, and then the initializers are the actual thing. So the comparison followed by the actual values. So it's going to take everything in this vector and initialize it into the priority queue. That's what the syntax does. And so the things in the vectors are the heads of the individual linked lists. All right, so that's our main data structure. So then we're going to need a main loop. So while queue is not empty, we're going to do something. So we're going to need a few things. So since we're combining linked lists like a zipper, it's usually easiest to make like a dummy head node, and then everything in your output is added as like onto the next pointer of that head node. It works out to be a little bit easier to reason about, as a instead of trying to account for stuff at the end, and it's a little easier to keep track. So I usually like to do that. So list node head, and it needs to be not a pointer because it doesn't exist yet. So we need to declare that first and separately from what I'm going to do next, which is declare some pointers. So for example, we have the head, which is the very beginning, and then we're going to need the current pointer. So where is the zipper at currently? And that's going to be equal to the head node to start off. And then lastly, I'm going to need like just a temporary variable to hold whatever we just popped off the queue. Because when it's not on the queue, we might want to increment it and put it back on. So we need to still keep track of it. So it's like a temporary variable. Don't need to initialize it yet because I'm always going to give it a value before using it. So node equals queued up top, and then queue.pop. And in C++, I don't think it really does it in one call. Like some other languages might. This pop function returns void, so you have to call top separately. And so since up here we were making sure that the nulls always floated to the top first, I'm going to check for that here. So if not node, continue. Yeah, so this will take care of all of that. Now, another option that might, it kind of depends. So when we eventually put things back onto the queue, we could also check there if they're going to be null. That wouldn't account for these like initialized null values that the inputs give us. So it's kind of 6 of one, half a dozen of the other. Do you want to potentially put a couple of null values, potentially up to k null values onto the queue, and then have it deal with that? Or do you want to check for those ahead of time? Yeah, so do you want k logarithmic time operations versus O of n constant time operations? It's kind of, well, what's going to actually be, there's no real way to know what's going to be worse. And either way, neither is going to increase asymptotic complexity. So now we need to actually add things to our output. So current next equals node. Let's adjust there, some tabbing, make it a little cleaner to read. And then we need to increment the zipper. So current would be current equals current next. But since we just, that's equal to node, so it's the same thing here. This is incrementing the zipper. And then lastly, we need to put the next incremented individualized list head back on the queue, so then that'll take care of finding whichever one's next. So queue.push, and that's going to be node. Oops. Node.next. And then this, at the end of each of the lists, this is going to be a null, but then we'll take care of that in the next iteration with this continue function. So then what do we need? We need to return the output. So head is not a pointer, so we use a dot. Is anything missing? I think that might be it. So first I'll talk about the complexities, and then we'll step through an example. So the complexity is going to be overall O of n log k runtime and O of k space. Now, why does it do that? So we're going to have O of n steps, and that's going to go through every item in all of the linked lists. So there, we want our output to be the same size, just sorted, as the input. So there's really no way around doing at least O of n things. Now, so we got an O of n factor. But for each of those, we're doing two priority queue operations, basically. Well, so there's the one to start, and that's O of k here. But then for the O of n, so there's O of n steps in this while loop, and each of those we're doing a pop and a push. Each of those is O of log k. So the total is O of n log k. But for space, I think this priority queue constructor and pushing and popping, I think that does a copy yeah, I think it is a copy constructor. I don't think it's a move constructor. So in that case, we are going to be doing O of k space, since there are k things in the heap. Up to yeah, so that's pretty much the space complexity we're looking at, which is still, it could be better than O of n. There's really no way to know, so that's why we denote it as k. It's certainly no more than O of n. Well, unless it gives you a bunch of null values, that'd be silly, but those will get taken care of at least. Okay, so now let's step through an example. Let's go with this. Okay, so we've got our comparison function. We set up our data structure, set up some temporary variables, and then the main loop. So node q.top, q.pop. Well, in the initialization, we put these things on the queue. So which of these is first? Like I said, I'm not actually totally sure if it's this one or this one that's on top. For our purposes, it doesn't matter because it's sorted, and we don't necessarily care about preserving the order of equal things in this particular case. Sometimes you might, we don't here, so I'm not gonna, that's not something that needs to be accounted for. So output, let's say it's on the left. We're gonna pop that off the queue. It's not null, so we're gonna not hit that continue. Add it to our output with current.next. And then we increment our thing, our zipper, and we push it back, push the next item on the queue. So next iteration, this one here is now on top, so we're gonna pop it off. We're gonna not continue, add it to our output, increment our zipper, and then push it back on the queue. Push the next thing on the queue. So there. And then next iteration, 4, 3, and 2. So 2 is now at the top of the queue. We're going to pop it off, not continue, add it to our output, and then increment our zipper, and then push the next thing on the queue. So we got a 6. It's now 4, 3, 6. Next iteration, 3 is on top, pop it off, skip, add it to our output, so 3. Increment zipper, push the next thing on the queue, 4. All right, 4, 4, and 6. Let's say this was already there, so maybe that stays. Anyway, so pop it off the queue, not continue, current, add it to our output, push the next thing on the heap, and increment zipper. So 5, 4, and 6. So this other 4 is now what's on top. So this is where it's going to start to get a little more interesting. So we pop it off the queue. We're going to not continue, add it to our output, increment zipper, push its successor on the queue. So we're going to push null onto the queue. Next iteration, null is now on top, so we're going to pop it off, and we're going to continue because it was null. So now we have two things on the queue, 5 and 6. 5 is the top one, so pop it off, not continue, add it to our output, increment zipper, push its successor on the queue, so null. Next iteration, null is now on top, so we pop it off, and then continue. So one last one, 2 more iterations to go. 6, pop it off, not continue, add it to our output, increment zipper, and push its successor on the queue. So star, and then last iteration, it's not empty, so we're going to pop it off the queue, and we're going to continue. We're going to see that the queue is now empty, so that's it. We'll break out of the loop, and then we'll hit our return statement. So 1, 1, 2, 3, 4, 4, 5, 6. 1, 1, 2, 3, 4, 4, 5, 6. It matches our expected output. So hopefully there's no syntax errors. Let's give it a run. Okay, yeah, full disclosure, I've done a few takes of this. This is correct because it relies on the priority queue / min heap setup. And it relies on the inputs being partially sorted to get a slightly better than O of n log n runtime. So since we have a smaller queue, so for example, it's asymptotically the same to do just a full sort as opposed to pushing everything onto a priority queue and then popping it off in order. Now that's gonna be, it might have an extra constant factor to use the priority queue method, but we can get better asymptotic properties because we don't need to have all of the input in the queue at a time. We are limited by the number of lists, so it's a little bit better that way. And I think that's everything. So check the nulls. Okay, we handled null cases. Okay, submit. And again, so these rankings don't really matter because it's as much about luck as anything, because it's a cloud service that does it, the compute, and then like you could just do it a few times to get maybe a warm cache. Anyway, so we are going to mark off the solution and then call it done. Thanks.